Hi, today you're going to learn about colligative properties, and I'm going to use the slides that are on Schoology to walk you through each one of it, and I'm going to cover all the essential points that you need to know. If you have any questions, please feel free to email me, and I'll answer them as quickly as possible. I will also be in my room during tutorial tomorrow. All right, so let's first talk about what colligative properties mean. What colligative properties basically mean, and I'm going to say this in the simplest of terms. Pretend you have a beaker of water. Now pretend you have a second beaker with water and some salt added in it. Kind of like what you did for activity 13. You just took water and you added salt to it. Now what colligative properties means is that if I compare, say for example, the boiling point of just pure water and the boiling point of salt water, they're going to be different. Pure water boils at 100 degrees Celsius, and salt water is going to actually boil at a different boiling point compared to pure water, and that just simply adding the salt and making water a solution made its properties different. Same with the freezing point. Freezing point as a colligative property simply means that if I took pure water and I tried to freeze it by putting it in the freezer, and then let's say I had a separate beaker of salt water, and I took that and put that in the freezer, they will both freeze at different temperatures. So water will freeze exactly at 0 degrees Celsius, and salt water will freeze at a different temperature. So let's figure out why this happens. Let's start with boiling point. So with boiling point, it actually goes up anytime that you add salt or sugar or basically something that dissolves in water. The boiling point is going to go up. And the reason that the boiling point is going to go up, let's use this diagram here to understand why the boiling point would go up. So I'm going to get this pen here. So consider this solution over here. We know that this is an H2O molecule because it's got two hydrogens and an oxygen. And we know that for water to evaporate, this H2O molecule, or to boil, this H2O molecule has to become a gas. So imagine if this beaker had only H2O molecules. The blue dots, let's pretend that's like salt or sugar that we added into water and dissolved it. So let's say this is like a sugar syrup. So if we had plain water without the sugar in it, then in the place where you see all of these blue molecules, you'd instead have another water molecule, right? And that would be easy to just boil off and go its own merry way. So if I add sugar to water, what I'm basically doing is this is going to now block the path of, let me change the color. Let's use something bright here. So this molecule, by existing here, what it's doing is it's blocking, say for example, this molecule of water, if it wanted to evaporate, it's going to be blocked off. Let's say if this molecule of water wanted to evaporate, it's going to be blocked off. So what the sugar is doing is it's basically blocking water from evaporating, but not all of the water though. Notice how some of them are still able to escape. And eventually these will be able to escape as well. They just have to work their way around the sugar molecule. So what happens is whenever you add sugar to water or salt to water, or basically dissolve anything in water, what you're doing is you are putting these solute molecules on the surface of the solution, and you're preventing the solvent molecules from vaporizing, which means that this will raise the boiling point of the liquid, because now suddenly you have to put more heat, more energy, and give these water molecules more strength to leave their hydrogen bonds and to become a vapor. So just by adding salt or sugar into water, you can actually raise the boiling point of water. And we call this property simply boiling point elevation. The word elevation means to bring something up. Now you don't have to do any problems with this formula, like no mathematical problems involved. But the reason I'm showing it to you is because I want you to understand if you had to calculate the boiling point elevation, how would you do it? So in this formula, this delta TB over here, delta simply means change. So don't be intimidated when you see the symbol delta in science, not just chemistry, even in physics. It simply means change. That's all delta means. It means change. So that means we know that water's boiling point is going to go higher than 100 degrees Celsius. The question is how much higher. It might be 2.3 degrees Celsius higher or 5.4 degrees Celsius higher, for example. It's just simply the change. The small I is something called a Van't Hoff factor, which is simply the number of particles. Hold on to that thought of Van't Hoff factor. In another slide up ahead, I will show you exactly how to find the Van't Hoff factor for something. And that's about the amount of math we're going to ask from you for this particular unit, is how do you calculate the Van't Hoff factor. Now, Kb is a constant. It's called the Molal boiling point constant. It's usually a given number, and it's, as the name suggests, like think about what the word constant means. It means never changing. So depending on what solvent you're using, the constant is always going to be same. For example, the Kb of water is always going to be this number no matter what. But if you did a different solution, say for example the Kb of alcohol, will always be a different number, but it'll be that same number for alcohol. And then little m, you already learned this last class. You even made a solution and found its molality. Little m stands for molality of the solution, and you know that's how we measure concentration of the solution. So here's something I want you to get out of this page. Out of this page, I want you to understand that the change in boiling point is related to the concentration of the solution. So listen to this important rule. If you increase the concentration of the solution, you will increase the boiling point even further. So more concentrated a solution is, the higher the boiling point is going to be. If you instead, say for example, let's consider a different scenario. Let's say we instead lower the concentration of a solution, which means we add less salt or less sugar, then the boiling point change is also going to be smaller. Excuse me. You can also change the freezing point, except instead of elevating the freezing point, adding salt or sugar to water will end up decreasing the freezing point. So every time, like consider these two beakers. Like let's say the beaker here on the left is just normal water. And let's say all of those green dots are water. So in a normal liquid, we know that the solid particles can easily melt into liquid, or the liquid can freeze into a solid because there's nothing getting in its way. But let's consider adding now a solute to it, like salt or sugar. What these solute molecules do, just like with boiling point, is they start to block the other water molecules from joining in to form ice, for example. So if you add salt to water, you're actually going to lower the freezing point of water, and we call that freezing point depression. In places that it snows very regularly, and there is a concern that because of the snow, the roads are going to freeze over, driving in ice is very dangerous. So what the road crews will do early every morning is they'll sprinkle salt on the roads, so that what the salt will do is it'll mix with the water that's in ice, and it'll lower the freezing point of water, which means that the water will stay as a liquid instead of turning into solid black ice. And that means that drivers now only need to drive on wet roads rather than icy roads. So the reason workers sprinkle salt whenever it snows on the pavements or on the roads is because salt does something called freezing point depression, which means it makes the water freeze at a colder, even colder temperature. All right, so looking at this picture, once again, I want to emphasize freezing point depression means we're lowering the freezing point, which means that normal water, for example, might have a freezing point of 0 degrees Celsius. So let's say the beaker on the right has a freezing point of 0 degrees Celsius. Or sorry, the beaker on the left has a freezing point of 0 degrees Celsius. Now the beaker on the right, because it has all these new solute particles that are blocking water from becoming ice, is going to have a lower freezing point. So the freezing point of this might be, I don't know, say for example, -8 degrees Celsius. It means that the freezing point has gone down by 8 degrees. And the reason the freezing point goes down is because now you have to take away even more energy. Like, remember, lower temperature means less energy. So the more you lower the temperature, the less energy the water molecules have. And if they have less energy, then they can't move around wildly in the beaker. They have to settle down calmly into forming ice. So just like boiling point elevation, we have a similar equation. Notice how it's almost the same. It's just instead of TB, you have TF to denote that this is the change in freezing point. But notice how you have delta, the Greek symbol for change. So again, here delta, it means change. Notice how you have I showing up again. And we haven't talked about Van 't Hoff factor yet. We're about to talk about it here in the next couple of slides. Van 't Hoff factor is the number of particles. Then you have the same thing, molal freezing point constant. Remember, this is a constant for any liquid. So for example, for water, it's always going to be -1.86 degrees Celsius per molal. For alcohol, it might be a different number. And then again, you see molality of the solution here. And remember, same as last time, if the concentration is higher of any given solution, then the change in the freezing point is also going to be higher. All right, so now we're going to talk about the Van 't Hoff factor. So the Van 't Hoff factor is based on how many particles are in the solution. And when you think about number of particles in the solution, think about a concentrated solution versus a dilute solution. You made both of those last class. You made a concentrated solution and you made a dilute solution. Think about the change in the food coloring. The concentrated solution looked darker and the dilute solution looked like the color had faded a little bit, right? That's because in your concentrated solution, you had more particles of food coloring in a very, very small amount of liquid, like just 50 milliliters of liquid. But in your dilute solution, you had less particles of that food coloring that were dispersed all over. That's why it looked lighter. So a concentrated solution is obviously going to have more particles. So that's why concentration matters when it comes to talking about freezing point elevation or depression. Now, the Van 't Hoff factor depends on what we're dissolving in water. So let me give you a few sample calculations for Van 't Hoff factors. Like, how can you tell the Van 't Hoff factor? So I'm going to take 4 different salts. We're going to do lithium chloride, barium chloride, aluminum sulfide, and aluminum phosphate. And what we're going to do is we're going to find the Van 't Hoff factor for each and every one of these. So we're going to represent the Van 't Hoff factor using the letter I. And so let me put the letter I for each and every one of these so we can write what we find as soon as we find them. At this point of the video, if you're really trying to review for this exam, you might want to pause it real quick just so that you can find out what the formula for lithium chloride, barium chloride, aluminum sulfide, and aluminum phosphate is. Because to find the Van 't Hoff factor, you must have the correct formula for each and every one of these. So to find the formula of lithium chloride, I know that lithium has a +1 charge. And I know chlorine, has a -1 charge. So if I do the crisscross between the two, I crisscross lithium's charge and chlorine's charge, I just get lithium chloride is LiCl. Now to figure out the Van 't Hoff factor, all you have to do is look at how many ions did you have to use in total to make this molecule. So let's think about how many ions I needed to make lithium chloride. I needed the lithium ion and I needed the chloride ion, and that's it. I just needed these two. So my Van 't Hoff factor for lithium chloride is 2 because I needed 2 ions to make it. Let's look at barium chloride. For barium, I know that my charge, because it's in group 2, is going to be 2 plus. Instead of 1 plus, now barium is going to be 2 plus, which means it has a positive 2 charge. But when I think about chloride, chloride is still in group 7, which means chloride still has a negative 1 charge. Let's look and see if our charges cancel out. They don't, because I have plus 2 and I have negative 1, which must mean I need another chloride ion to make this work. So I have plus 2, and now I have 2 negative charges, so I have negative 2. So we know that the formula for barium chloride, instead of just how we did lithium chloride, is just LiCl. You cannot do barium chloride, it's just BaCl. It ends up being BaCl2, since I needed 2 of these. So now let's count how many molecules, how many ions did we end up using for it? We used 1, 2, 3. So we used 1, 2, 3 ions, so my Van 't Hoff factor for barium chloride is 3. Now let's try to figure out the Van 't Hoff factor for aluminum sulfide. So for aluminum sulfide, if I try to look at the formula, I see that it's aluminum is 3 plus, and sulfide, which is just sulfur on your periodic table with a charge, has a negative 2 charge. So if I do my crisscross and move my charges on opposite directions, I'll get my formula as Al2S3. And if you count how many particles Al2S3 has, it says I have 2 aluminum particles, 3 sulfide particles, so now I have a Van 't Hoff factor of 5. You can do that with any formula, like lithium chloride. I have 1 lithium, 1 chlorine, 1 plus 1, 2, so my Van 't Hoff factor is 2. Barium chloride, I have 1 barium, I have 2 chlorides, 1 plus 2 is 3. And for aluminum sulfide, I have 2 aluminums, I have 3 sulfides, 2 plus 3 is 5. I'll let you figure out aluminum phosphate. Remember, for phosphate, you have to go to your common ions that you memorized in order to figure out what the formula is going to be. Try doing it and see what Van 't Hoff factor you get. Compare it with some of your friends to see if you got the same Van 't Hoff factor. All right, we've seen this phase change diagram once before. Notice how this phase change diagram changes depending on whether or not you're adding basically any sort of salt to it or sugar, whatever it is you're adding. So the normal normal boiling point and freezing point, you can see that over here along the green line, which now I'm painting over with yellow. That's the normal boiling point and freezing point of a particular solvent. Notice how adding something like salt pushes it back. It pushes it further back, so the freezing point becomes lower, and this one gets pushed forward, which means the boiling point becomes higher. All right, let's look at this practice problem. A worker is going to salt the roads to prevent freezing. Remember I said that whenever it snows, we can add salt to our roads, like just sprinkle salt all over it, and it will prevent the roads from icing over. And he's trying to decide between sodium chloride and magnesium chloride. Which salt should the worker use and why? And how does adding salt help with the road? So let's first figure out which salt the worker should use. So he's trying to decide between sodium chloride and magnesium chloride. So let's first figure out what is the formula for each of these. So sodium chloride, we know, is Na plus and Cl minus, which means our formula ends up being NaCl. And magnesium chloride, since magnesium has a 2 plus charge and chloride has only a -1 charge, it's going to end up being MgCl2, since magnesium had a +2 charge. So let's think about the Van 't Hoff factor in each one of these. I have sodium and I have chloride. So here my Van 't Hoff factor is 2. Here I have magnesium and I have 2 chlorides. So 1 plus 2, my Van 't Hoff factor here is 3. So which salt should the worker use? If I were the road worker and I had magnesium chloride available to me, I would use magnesium chloride because it gives me more particles per molecule. Like I can get 3 whole particles instead of just 2 particles that sodium chloride gives, which means that the freezing point of water goes down even further, which means I need an even colder temperature to freeze water so the roads will stay safe even at a lower temperature. Now, how does adding salt help with the roads? The addition of the salt prevents the water molecules from freezing because the salt gets in the way, which means that more heat must be removed, which means that the temperature has to get colder in order for water to freeze, and it would lower the freezing point. So this keeps the roads from freezing and keeps our drivers safe. All right. I hope you were able to follow along with this lesson. If you weren't, please send me an email. Try answering the questions on colligative properties in your homework packet. Today, for the rest of the class, you should be done with the entire homework packet, worksheets 4, 5, and 6, so that next class when we meet, we can get it signed off. I will be a tutorial tomorrow for you to ask any additional questions that you might have. Hope you have a good rest of the day.